Hello, everybody. I will be doing my lecture number 14 in a series of linear algebra. Um, this lecture is all about orthogonal vectors, orthogonal subspaces. So basically, it's about orthogonality. It's a very important concept in linear algebra and also in most of the signal processing concepts and communication concepts. So let us look into how we define orthogonality and how we can make sure that we have the right vectors, that we call them orthogonal vectors. I will share my screen right now. And we will move towards what is known as the Gilbert Strand MIT lectures. And I will be trying to explain what an orthogonality means. But before I go into this, I would like to describe what is being shown on the picture right now. There is um, a row space, null space, column space, and what we call left null space, or we can say null space of A transpose. Now keep in mind these all four spaces are associated with the matrix AX equal to B. So they are associated with the matrix A, which is we call them the coefficient matrix. So keep in mind that AX equal to B is representing a linear system of equations. So it's a system of linear equations. So there are more than one linear equation, and we are trying to solve them simultaneously. So basic underlying uh, theme is AX equal to B, and we're trying to find this unknown X. So keep in mind that based on the matrix A, we have four subspaces. Now, this row space and null space, actually it is a subspace of R raised to power n. And column space and null space of A transpose, these are subspaces of R raised to power m. Now, the order of the matrix A is m rows and n columns. So it is an m into n order matrix. So let us define what we mean by orthogonality. Before I go into this, let me state a fact, then we will prove it later on, that row space and null space, these two subspaces are orthogonal to each other. But they have one commonality, and which is that they both contain this zero vector. So zero vector is the intersection between the both spaces. So the only thing that is common between these two spaces is one point. Most of the time, it has this misunderstanding that maybe the row space and null space has a line of intersection, just like you have a wall and you have a floor. They intersect at one complete line. No. In case of row space and null space, when we describe them as orthogonal, or we can call them orthogonal complement, in that sense that they will have only the origin is the common point. So they only, these two subspaces, if you look at them geometrically, they only intersect at one point, and which is the origin. Similarly, the column space and the left null space, we call null space of A transpose, they also have the intersection at the origin. So they only contains this zero or the origin common between the two spaces, not a line, not any other. So they only meet at one point. They are orthogonal, or in some sense they are perpendicular, and they join only at one point. Keep those facts in mind, and let's move forward. So let's go and look at the dimensions we're talking about. So from the dimensional analysis point of view, if the row space has a dimension R, if the row space has a dimension R, then the null space will have the remaining dimension of R raised to power n. So the remaining dimension is n minus r. So whatever the dimension of row space and whatever the dimension of null space, if you add these both dimensions, they should be equal to the dimension of the space from which they are the subspaces. So it is the space is r raised to power n. So similarly, the column space and the left null space, they are subspaces of r raised to power m rather than n. So in that space, the column space dimension is always same as the row space dimension. So if this is r, then column space will also be r, and the remaining dimension for the left null space is m minus r. So this is a bit convenient when we are trying to find the dimension or the basis of these subspaces. So these two, row space and null space, will give you the whole r to the power n. Column space and left null space together will give you the whole r raised to power m. So what I'm saying is right now is that if you have a vector in r raised to power n, then either it will lie entirely in row space or it will lie entirely in null space, or some part of it will be in row space and some part of it will be null space. So if you add those two parts, you will get the complete vector. Or in vector analysis language, I can say that the components of the vector will be split between these two spaces. So similarly, a vector in r raised to power m will be either in column space entirely with no component in left null space, or it is entirely lying in the left null space with no component in column space, or another chance is that it has some component that falls into column space and some component that will fall in the left null space. So that is how we look at a vector by splitting it into its part that belongs to different subspaces. Now, once we say that the two vectors are, once we say that two vectors are orthogonal, what we mean by this? So when we say two vectors are orthogonal, we have to look at this right angle triangle, Pythagoras theorem. So this is a very good example of orthogonality. So the Pythagoras theorem basically says that, and I will just quote Gilbert Strand, which is that if you have a right angle triangle where you have one vector x and then there is another orthogonal vector y, and then we have a resultant vector x plus y which goes from tail to head. Now in that situation, the distance along this x, what we call them the length of x, which is the distance along x vector squared plus the distance along y vector squared, should be equal to the distance along their resultant, which is x plus y whole squared. Now, this is a Pythagoras theorem, or we can say the equation that has been used over the years, where we say the distance of one side squared plus the distance of the other side squared is equal to the distance of hypotenuse square. So this is a relationship, but keep in mind this relationship is not an identity. This relationship is an equation and it is only true under certain conditions. So let's look into those conditions. But here I would like to emphasize the notation. Look at this. The way a distance of a vector is defined is by two vertical lines to the left and two vertical lines to the right. This basically, when encapsulates a vector between them, this represents a distance. Sometimes we call them norm, but let's shy away from using another complicated word, norm. So we will say that this is a distance. So to represent a distance in mathematics, and sometimes we use those vertical bars, two vertical bars to the left of that, and two vertical bars to the right of that. This represents the distance. So the distance of x is represented by these vertical bars. Similarly, the distance along y is represented by these vertical bars, and the distance along x plus y. So keep in mind x plus y representing a vector, and this has also have bars. So the distance along x squared plus distance along y squared is equal to distance along x plus y squared. Now, if you look into this equation and try to make sense out of it, we will see what we mean by these equations. Now keep in mind, and that is very important, that what we mean by these, so what we mean by this distance squared. So the distance squared in language of vector algebra, we can write that this is equal to x transpose x. So this squared thing, the distance squared thing is translated to x transpose x. Now keep in mind, when we talk about a vector in linear algebra, we talk about a column vector. So this x transpose will make it a row vector. A row vector, when multiplied with a column vector, it always give you a number. So this number is representing the distance squared. So this distance squared is represented by this particular vector algebra, x transpose x. Similarly, this y can be represented with y transpose y. And this x plus y distance squared can be represented by x plus y transpose into x plus y. So you can imagine what is going on here. So now look at it. On left hand side, we have x transpose x plus y transpose y. So these two terms are there, and these two terms are representing these two distance terms, and equal. And now for this particular distance term, we have to do x plus y whole transpose into x plus y. When you open this, now you apply the transpose, so this becomes x transpose plus y transpose. And now this x transpose plus y transpose will multiply with x plus y. So you get four terms. First term is x transpose x plus y transpose y. The next term is x transpose y. And then you have the fourth term, which is y transpose x. If you look into this equation on the left and right, these two terms are cancelled by these two terms. So we have on these two terms on the left, we have the similar terms on the right. Now these two cancel. Now keep in mind, these two, y transpose x and x transpose y, they are both same because they give a number and this give a number and this give you the same number. So we can eliminate these two terms and represent them by only one term. So we'll put a 2 in front of it. So this becomes 2 times x transpose y. So if you do look into this, so you see, you have now at the end of the day, from this Pythagoras theorem equation, we get 2x transpose y equal to 0. Of course, 2 cannot be 0. So this 0 is actually coming from x transpose y, this particular number to be 0. And this number can only be 0 if we are sure that x is orthogonal to y. So when we have an orthogonality between two vectors, then x transpose y or y transpose x will give you a 0. So this is the basic conditions behind. So Pythagoras theorem can only be applied at right angle triangle. And when we say right angle triangle, then we say that one side is perpendicular to the other side. Or in the vector language, we can say that one vector is orthogonal to another vector. So orthogonality is represented in linear algebra by using x transpose y equal to 0 or y transpose x equal to 0. So this is the one particular conditions we have right now. Now let's extend this concept of orthogonal vector to orthogonal subspaces. So once we say that a subspace S is orthogonal to another subspace T, keep in mind these both subspaces live in another, it lives in the same space. So these two subspaces belongs to a space and they are subspaces, just like subset. So these are subspaces. S is a subspace of a particular space and T is also the subspace of the same space. They both belong to same space, but they are subspaces. And we wanted to know whether these two subspaces are orthogonal to each other or not. So for orthogonality of a subspace rather than a vector, it is important that every vector in subspace S should be orthogonal to every vector in subspace T. So let's check that condition. So what we are saying, so what we are saying here is that once you say that every vector is in subspace S is orthogonal to every vector in subspace T. Let us take the example of the wall and the floor. Now we are saying that these are not orthogonal subspaces. If you consider wall as subspace S and you consider the floor as subspace T, then these are not orthogonal, and I will tell you why. So the argument is that let us say that you have a vector at from the origin and it is at 45 in the wall. So you know that in linear algebra, every vector has to originate from the origin. So let's say that the wall and the floor, they have a origin at the corner. So where they meet, there is an origin. So from this origin, if I extend a vector at a 45 angle in the wall, then this vector is not orthogonal to every vector on the floor, because every vector on the floor will also start from the origin, but it will be lying on the floor. So the angle is not between them, this 90 degrees. So they are not perpendicular. So it means that for a one surface, if we declare that geometric surface to be a subspace, it has to meet another surface only at the origin. It should not have an extended intersection. Like in case of wall and floor, they have a complete line of intersection. They meet at a seam line, a crack line between them. So in that case, they are not orthogonal. Orthogonality of subspaces basically requires that they should be meeting at one point, and that point is the origin point. So, so now what we are saying is we are claiming that the row space is orthogonal to null space. Now, when we say row space is orthogonal to null space, it means every vector in the row space is perpendicular to every vector in the null space. Now, what is a null space? We all know that the null space is all those vector x which satisfies the equation a matrix A times this vector x equal to 0. So all those x, once they are transformed by this matrix A, they end up in 0. If their B in this case is 0, then those x, we declare them as our null space inhabitants. So our null space is made from those x. Once they are transformed, they give you 0. So it means all of them after transformation lose their identity and fell into that black hole which exists at the origin. So if you draw, if you write that equation, we will say row 1 of A, row 2 of A, row M of A. So there are M rows of the matrix A, and they are multiplying with this vector X, and they are giving that M number of zeros. So first row multiplied with this vector X gives you first zero. Second row multiplied with this X gives you the second row. And similarly, the mth row multiplied with this whole X and give you. So it means this X is orthogonal to row 1 because it is giving you 0. Dot product, in some sense we call them inner product. Similarly, this X also once dot with row 2 of A also give you the second 0. So it means X is orthogonal to row 2. Similarly, X when dotted with row M give you the last 0. So it means this X, which happens to be in the null space, is orthogonal to all the rows that are present in that particular matrix A. So all those rows are basically making your row subspace. So this particular X, which happens to be in the null space, is actually orthogonal to the row space. So all this basically completes the argument that if there is a vector which lies in the null space, then that vector will be perpendicular or orthogonal to everybody in the row space. So because it is perpendicular to all the basis vectors, if all of them are independent, then we can declare those rows as our basis. So if X is perpendicular to basis, so it means that X is basically perpendicular to the whole row space, which is made from this row basis. So in that way, if a vector happens to be in the null space of a matrix, then that particular vector is orthogonal to the row space associated with that matrix A. Now, if you look very closely into uh, the other aspect of this matrix, when we say orthogonal, we have to really understand uh, what we mean by orthogonality. So let us say you have a space R to the power 2. In that case, if that is the space, then the row space will be a line, and the null space will also be another line, because the dimension of the null space, which is a line, is 1, and the dimension of another line which we declare as our row space is also 1. So if you add 1 plus 1, it will complete the dimension of R to the power 2, from which these two subspaces are made, to which these two subspaces belong. So if you take an example, that will be really nice, where we can show what we mean by the row space and column space. So let me take you back, and let's look at this matrix A. So let's say the matrix A is, the first row is 1, 2, 5, and the second row is 2, 4, 10. One thing you can see very clearly here, that it contains two rows, but these two rows are not independent, because we can make very easily the second row by just multiplying the first row by a scalar 2. So if I multiply this number 2 with these 1, 2, 5, I will get 2, 4, 10. So in other words, um, it has the rank 1, because the rank actually represents the number of independent rows. So in this case, the independent rows here are only 1, because the next row can be made very easily from a scalar multiple of first row. So this row is not independent, and it cannot be declared as part of the basis, and similarly, it is not part of the rank. Rank is the number of independent rows or independent columns. Similarly, if you look into the columns 1, 2, 2, 4, 5, 10, the first one is the column that we are looking for, because the next two columns can be made very easily from the first column. If I multiply 2 with the first column, I get the second column. If I multiply 5 with the first column, I get the third. So it means this matrix A has only one independent column and it has only one independent row. Keep in mind, the rank is the number of independent columns or the number of independent rows. Both should be same. So in this case, R is 1. Now, once we say for matrix A, the order is M into N. M is the rows and N is the column. So here is the columns are 3. So let us look at the dimension of the null space of A. Now, what is the dimension of null space of A? Now, keep in mind, we have to complete R to the power N, which in this case is R to the power 3. So it's a 3-dimensional space, and we need to find its row space and null space. Now, once we know that the row space dimension is 1, because the rank is 1, then of course, the rest of the dimension, because it is R to the power 3, so 3 minus 1, the rest of the dimension, which is 2, should come from the dimension of the null space. Because as I told you, that the null space dimension and the row space dimension, if you add them, should be making the dimension of R to the power N. And in this case, R to the power N is R to the power cube. So it's a 3-dimensional space that is made from row space and column space. So you should keep in mind that this is how the dimensionality analysis works for linear algebra equation or system of linear algebra. Okay. So since we know that the second row is completely dependent on the first row, so it does not give us any more help. So we can entirely remove it. Even if you remove it, it will not change the whole equation or whole information. So n will remain 3. So there are 3 columns. Rank will remain 1. Okay. And the dimension of the null space will remain 2. Although we have removed the second equation, but still it has the same amount of information. So it means the dependent rows or the dependent columns does not add any new information as far as solving that system of equations is concerned. So if we are really wanted to add information for the solution of the system of equations, we need to really add independent rows or in some way independent columns. So this is the whole idea behind it. So let us look into another term we sometimes use. We call them orthogonal complements. So we can say that the null space and row space are orthogonal complement in R to the power n. Now, why we are saying that these are orthogonal complement? The reason is we feel that the dimension of null space, if you add to the dimension of row space, that should be equal to the dimension of the space from which they came. So it should be equal to n. So the dimension of null space plus dimension of row space should be equal to this letter n. That is why it is called these two spaces are orthogonal complements to each other. We sometimes write this with this symbol. You can see the symbol is there is a horizontal line and there's a vertical line on top of it. So these are perpendicular. We call them orthogonal also. So now what is important most of the time is we are trying to solve a system AX equal to B, but there is no solution. And one reason for that no solution is sometimes that the A is not a square matrix. A is a rectangular matrix, or we sometimes call it tall matrix. This is a very practical situation, because what happens is that in some cases, or I will say most of the practical scenarios, you are getting a lot of measurement. And every measurement that you get will give you a linear equation. So if you have a lots of linear equations and you're only solving few parameters, so it means that your columns are less and your rows are enormous. Let's say you have 500 rows and your columns are only 2. So you have a 500 into 2. So in that situation, it becomes a very tall matrix. So A is a very tall matrix, whereas you're only trying to find, let's say, the slope and y-intercept. But to get a slope and y-intercept, you have 500 points. You're trying to fit that line through these 500 points. Now, how to do it? If you use elimination, what will happen is we will end up in a no solution, because when you do elimination, you will get 0 on one side and you will get a non-zero number on the other side. This will tell you that this particular system has no solution. So if this system has no solution, or in other words, the A is a tall matrix and you're trying to solve AX equal to B, the best we can do is we can look into how to make this AX equal to B a square matrix. So for making a square matrix, what we will do, we will play a trick. We will multiply this A and what we call in linear algebra pre-multiplication, because we are multiplying it from the left-hand side. Because a matrix can be multiplied from the left and can be the right. So it has, and these two are not equal. So the order does matter when we are talking about matrix multiplication. So here from the left-hand side, when I am multiplying it, the matrix A with an A transpose, what happened is this A transpose times A, this will make this a square matrix. Now, once I remove this rectangular, transform this rectangular matrix into a square matrix, then there is a chance that I will get an inverse of this. And if I get an inverse of this, then there is a chance that I will get a solution to AX equal to B, because my unknowns are along X and the unknowns are less than the number of rows. So if you look into A transpose A, what you will find out is it is a square matrix. Now, if you look into the dimension of A transpose, it is n into m, and the dimension of A is m into n. So these m and m are removed, and we get n into n, which is a square matrix. Similarly, this A transpose A is also symmetric. It has these two properties. The moment I pre-multiply A transpose with A, I get these two nice properties, square matrix and symmetric matrix. And once you have a square matrix, then I think AX equal to B appears to have a solution. Now we, from AX equal to B, we transform it into this particular new equation, which is A transpose A X. Now A transpose is multiply on the left here. So the A transpose is multiply on the left to that side. So now we get an equation A, but keep in mind now this X and this X is different. So this X is an X hat. This is the best possible solution you can get, which is in a least square sense close to this X. So this is a least square solution. However, this particular system has no solution. However, this has a solution. But this solution is also dependent on certain conditions. This only has a solution if this A transpose A is a full rank. And this A transpose A will have full rank. When we say full rank, it means that all the rows are independent, or we can say that all the columns are independent, because it is a square matrix, rows and columns are same, n by n. So A transpose A will only be invertible if it is a full rank, and A transpose A is only a full rank if A has independent rows. And you know, once where we started from that A can have 500 rows. But if all those 5 rows are independent rows, none of the rows can be made from any other row. So in other words, what we are saying is if all the measurements are independent measurements, then there is a chance that we will be able to solve this equation rather than this equation. So A transpose A will be invertible. We take it to the other side. and then we will find x. So this equation will be solvable only if all the measurements we are taking, because every measurement is making a row of the matrix A, that particular measurement is independent of the other measurement, then there is a chance that we will be able to get a solution. So if I just continue with the video, and we will get some very nice examples. So what we can say is that the null space of, now for invertibility, you know that we can declare a matrix to be invertible only if its null space contains zero vector. If the null space has more than zero vector, then that particular matrix is not invertible. So the null space of A transpose A is exactly same as null space of A. In other words, the rank of A transpose A dependent on the rank of A. So if A is a good rank matrix, yeah. So if A is a good rank, full rank matrix, then there is a chance that the A transpose A will also have a full rank. And if it is a full rank, then there is a chance that it will have an inverse. And when it's an inverse, then we can solve this equation. So AX equal to B in most practical cases may not have a solution, but we can play a trick where we multiply with A transpose on left hand side and A transpose on left hand side on the B side, and we can maneuver and get a solution. But keep in mind, this solution is the best possible least square solution to the original problem. So I hope we all learned from the today's lecture what is an orthogonal vector, what is orthogonal subspaces, and how to solve a system of equation Ax equal to B where A is a tall matrix. With that, I will just uh, stop the video and my lecture 14 ended, and we will start with lecture 15 next time. Thank you very much. If you have a question, please drop me the comment under this YouTube, or you can go to Google Class and send me a comment there. Thank you very much, and we will see you